In this video, we will describe how free energy perturbation, or FEP, predicts binding affinity using the small molecule relative binding FEP method. To review, free energy perturbation is a physics-based computational method that simulates molecular motion at the atomic level. Scientists use FEP to calculate free energy differences within a system. Typically in thermodynamics, Gibbs free energy, or delta G, could tell us how energetically favorable or stable a system or reaction is. For our purposes here, the system is a protein bound to a small molecule drug. Delta G calculations allow scientists to understand a clearer picture of a protein's movement or conformational space and capture the complex physics involved in the binding of a molecule to a protein target. FEP is frequently used to predict the binding affinity of drug-like molecules. Binding affinity is equal to the change in the free energy associated with the binding process. We will come back to this. Computational prediction of protein-ligand binding requires determining the binding mode and evaluating the strength of a protein-ligand interaction. Such calculations require the structure of the small molecule binding site on the protein to be known. Now to narrow our focus a bit. Relative binding FEP is a specific method of FEP that uses what we already know about a reference protein-ligand complex to predict the binding affinity of a new similar ligand. It does this by performing an alchemical transformation. The term alchemical here describes the simulated transformation of a reference ligand into another ligand by changing elements, bond orders, adding or removing atoms. Now let's recall that binding affinity is equal to the change in the free energy associated with the binding process, or the delta G of binding. This means that to calculate delta G, we must model the binding process of each ligand into the protein complex to calculate delta G1 and delta G2. We now have ligand 1 and ligand 2 in bulk solvent, and each ligand bound in the binding pocket of the protein complex. Ideally, we could stop here, but unfortunately this binding process is too difficult to model. We are unable to reasonably calculate delta G1 and delta G2. This is because when calculating a change in free energy, the system size and scale of the change has a large impact on computational feasibility. A small change is easier to calculate, less expensive, faster, and more accurate, while a large change can be prohibited. Modeling this binding process is difficult because the change is large. Think of the size alone. A small molecule ligand transitioning to a full protein ligand complex will be computationally challenging. Thankfully, there's another way. We can instead compute the delta Ga of our reference ligand to the modified ligand, and the delta Gb of the protein complex transition, as these changes are reasonable. Then compute delta Gb minus delta Ga. Please take a moment and pause here until this concept makes sense to you, as this is a fundamental method of relative binding FEP. This video illustrates the concepts behind this calculation. Let's zoom into the thrombin binding site to a location where a water molecule is buried deep into the binding cavity. Here we can see that a chlorine substitution at this hydrogen position might improve binding affinity. To compute this, FEP slowly exchanges the reference ligand's hydrogen for chlorine in a series of discrete molecular dynamic simulations. We are able to follow the energetic impact of this change. You can think of this as carefully turning off the forces and interactions associated with the hydrogen while carefully turning them on for the chlorine. Molecular dynamic simulations provide us with a free energy landscape for each system and a better understanding of the energetically preferred conformational space for our complex. Ligand 1, ligand 2, and the protein itself are in motion, so the snapshots represent a slightly different conformation of each species. This series of discrete molecular dynamic simulations performed are known as lambda windows. This makes the change in energy states even smaller and more computationally feasible. Another concept that is important to be aware of for FEP is the use of dual topology. In order to mutate ligand 1 into ligand 2, a dual topology molecule, which has the physical attributes of both molecules, is used. The properties and forces on the new atoms are scaled across the various lambda windows, with ligand 2's atoms being invisible dummy atoms in the starting state of ligand 1, and ligand 1's atoms being invisible dummy atoms in the final ligand 2 system. We are going to switch gears a bit here and begin to reference Schrödinger's proprietary FEP technology, FEP+. FEP+ is widely adopted across the drug discovery industry to triage compounds for synthesis. Up to this point, we have only considered the process of mutating one reference ligand into a new ligand. This is known as single-edge FEP+. The edge is the single connection between the reference ligand and a new idea. Typically, when using relative binding FEP+, we will generate more complex perturbation maps, which have a number of connections between a number of congeneric ligands. The FEP+ interface allows you to easily create reference maps to connect these relationships. Increasing the number of reference compounds in the network is known as cycle closure FEP+. This can improve accuracy, but often increases simulation time, as you are essentially checking your answer by having multiple routes through which calculations are performed. This is often via multiple connections and intermediates to enable prospective prediction. There are many additional ways the FEP method can be used to answer complex biological questions, not covered here, as indicated by the various FEP+ workflows. The underlying concept in all cases is that we can use molecular dynamics to simulate the differences between a system in an initial state and a final target state. If you would like to learn more, we encourage you to check out Schrödinger's online course, Free Energy Calculations for Drug Design using FEP+, for more in-depth understanding as well as hands-on exercises. You may also find the linked case study beneficial for understanding how FEP+ was used at Schrödinger to identify potent and selective inhibitors. Thanks for watching.